Now it's time for the fifth and final universal science concept, which happens to be measurement uncertainties. Anytime you take a measurement, there's going to be error associated with it. That's why we assign an uncertainty, and therefore we say that it is fraught with error. Do you like that word fraught? I think you ought to start using the word fraught in everyday speech to revive the word. When you assign an uncertainty to a measurement, you're going to let the person know who's looking at your data how much you think your answer might be off. You're saying, I think this is the value, this is what I measured it to be, but it could be a little bit above or below that. So that's the whole point of an uncertainty, is to give the person an idea of how carefully you were able to measure. When scientists look at experimental data, they want to know if it's good data or not. And so, if I say the length of the pencil is 10 centimeters plus or minus a tenth of a centimeter, that tells me I've measured it pretty well. If I say it's 10 centimeters plus or minus 2 centimeters, that's like, did I even bother measuring it if I'm not sure within 2 centimeters either way? So this is why we use uncertainties, to give a scientist who's looking at our data an idea of how carefully we measured things. If a person is looking at your data and they realize that it's weak data, then why would they bother to even want to look at what you've done? Because if the data wasn't well taken, then the results are not good results. Good data gives you good results. Bad data gives you pointless results. So the question that we're talking about today is what makes things have uncertainties? What causes this error? And then how do we deal with it? So we're going to start with the 3 causes of uncertainty that we have in measurements. The first one is the measurement technique we use. Here what I'm trying to illustrate for you is someone putting a ruler down and then putting their finger in place and then moving the ruler over and then moving their finger at the end of that and then moving the rule over. That is not going to be a very accurate measurement technique. Look how far apart the ends of those rulers are. So that kind of measurement technique is going to give you poor results. Whereas if I say use a measuring instrument that is as long as that needs to be, now I don't have all that error in there. Or if I lay I have 3 rulers and I'm able to lay them end to end so that they're touching each other, that might make it a more accurate measurement. So the technique I use will affect how accurate the results are and therefore affect the uncertainty. The second thing that might affect the uncertainty is the instrument limitations that we have. If I'm going to measure the diameter of a pencil and I'm going to use a ruler, I'm going to get one kind of answer and it may not be very accurate. If instead I'm going to use a vernier caliper, I'll be able to come up with a much more precise answer because these jaws will clamp down onto the pencil and give me a really, really accurate reading. So the kind of instrument you have to use will affect the uncertainty. If I want to measure the length of the hallway out here and I do it with a meter stick, I'm going to get one kind of answer. If I use one of those wind-up tapes that goes all the way down the length of the hall, I'll probably get a much better answer and therefore much less uncertainty. The final problem that we have with uncertainties is if we're trying to measure something that is going to be awkward. So problems inherent with what's being measured. You see down here in the corner I have put a balloon. If I'm trying to measure, say, the circumference of this balloon or the diameter of this balloon, that's tough to do because the balloon will change shape and because the balloon is not flat, it's round. So any problems inherent with what I'm trying to measure will affect uncertainty. When we record uncertainties, what we do is we list the measurement. In this case, it's 26.4 centimeters, and then we say plus or minus the amount that we're uncertain. So 26.4 plus or minus 0.1 centimeters would be the length of something. We think it's 26.4 centimeters long, but it might be 26.5 or it might be 26.3. That's why we assign uncertainty of plus or minus 0.1. And as you can see, that's what this slide tells us here. So when you go to assign an uncertainty, what you're asking yourself is, could this measurement be as high as whatever or as low as whatever, I measure the length of the pencil, I decide it is, 11.2 centimeters. Well, could it actually be 11.3? If I say yes, then then I say, could it be 11.4? Well, no, I don't think it'd be 11.4. If I don't think it could be 11.4, then my uncertainty is plus or minus 0.1. If I think it could be 11.4, but not 11.5, then maybe my uncertainty is plus or minus 0.2. So that's kind of how you do it. So this uncertainty that I put at the end of a number like this is called the absolute uncertainty. So that's a new vocabulary word for you. The absolute uncertainty is the uncertainty that you actually assign to a measurement. This is a good time for me to point out to you that the absolute uncertainty must be to the same number of decimal places as the measurement. So 26.4 is plus or minus 0.1. 26.4 can't be plus or minus 0.05. If it's 26.4 plus or minus 0.05, then what you want to say is 26.40 plus or minus 0.5, so that both the uncertainty and the measurement are to the same number of decimal places. Okay, if we're going to add or subtract measurements, then all you're going to do is add or subtract the absolute uncertainties. It's really simple. For instance, here is a problem. What's the perimeter of our classroom if we measure its length to be 13.8 plus or minus 0.2 meters, and its width to be 8.6 plus or minus 0.1 meters? By the way, presumably we use the same measuring instrument for both of these measurements. Notice this one has a slightly bigger uncertainty than Notice that the first one has a slightly bigger uncertainty than the second one does. That is because the first one is a bigger number that we've measured, and the chances of there being a higher uncertainty when you're measuring something bigger are going to be greater. So that's why the uncertainties don't have to be the same, even though maybe we use the same device and the same technique, just because we have a bigger answer. So to get the perimeter, what we do is add length plus width, right? Because we have to measure the distance around the outside edge. So what I've done here is I've taken all the measurements, the length, the width, and added them together. And then separately, I have taken the uncertainties for the lengths and the widths and added them together. So those are done as two separate things. You add the measurements, and then you add the uncertainties, and you separate those two by this plus or minus symbol. So our result ends up being 44.8 meters plus or minus the 0.6 meters. Notice what we do is we put the meters out here at the end. So it's 44.8 plus or minus 0.6 meters. If we happen to be multiplying or dividing measurements, we can't simply add the absolute uncertainties, because usually when you're multiplying or dividing, you're not multiplying or dividing by things that have the same unit. So what we have to do is we have to figure out something called a relative uncertainty first. A relative uncertainty is a percentage uncertainty. What percent is the absolute uncertainty we assigned of the measurement that we originally took? So when you're multiplying or dividing, what you will do is you will add relative uncertainties, not absolute uncertainties. When we added and subtracted, we could add absolute uncertainties. When we multiply or divide, we add relative uncertainties. So let's see, how do we get a relative uncertainty? Let's go back to our original number, the 26.4 plus or minus 0.1 centimeters. Here is the equation for relative uncertainty. It's the absolute uncertainty divided by the measurement. The absolute uncertainty is the thing that's listed after the plus or minus, and the measurement is the thing that's listed before it. So the relative uncertainty is equal to 0.1 centimeters divided by the measurement, which is 26.4 centimeters, and then that whole thing gets multiplied by 100. So when you do that math, you end up with a relative uncertainty of 0.4%. What that means is that 0.1 centimeters is 0.4% of 26.4 centimeters. So that's all you're doing, is telling me what percentage the absolute uncertainty is of the measurement. So the way we're going to write it then is we're going to write it as 26.4 centimeters plus or minus 0.4%. What we do is we put the units with the measurement because the units of our relative uncertainty are percent. So with the absolute uncertainty, notice we put the units out at the end. So we could say the measurement plus or minus the uncertainty and then the unit. But with the relative uncertainty, we have to put the unit with the original measurement because the units of the relative uncertainty are percent. So 26.4 centimeters plus or minus 0.4%. So let's do this example. What is the speed of a car that goes 500 plus or minus 5 meters in 40.0 plus or minus 0.5 seconds? So you want to write that down. So first of all, because we're going to be dividing, speed is distance divided by time. What we're going to do is we're going to change that absolute uncertainty of plus or minus 5 meters into a relative uncertainty. So look what we did here. In place of plus or minus 5 meters, I put 5 divided by 500 times 100, or 1%. So 500 plus or minus 5 meters is the same thing as 500 meters plus or minus 1%. We have to do the same thing with the time, get its relative uncertainty. So I keep the measurement, which is the 40 seconds, and now I figure out the relative uncertainty by dividing 0.5 by the 40. The absolute uncertainty divided by the value, the measurement value. And then I multiply by 100. So 40 plus or minus 0.5 seconds is the same as 40 seconds plus or minus 1.3%. So when we're going to get the speed, it's distance divided by time. So we're going to take the distance with its relative uncertainty and divide it by the time with its relative uncertainty. But we don't divide the uncertainties. We just divide the measurements and we add the uncertainty. So this becomes 50 meters divided by 40 seconds plus or minus the uncertainties, the 1% plus the 1.3%. We just add those relative uncertainties. So when we do that division, we end up with 12.5 meters per second plus or minus 2.3%. If we wanted to, we could then convert that relative uncertainty back into an absolute uncertainty by reversing the process. We need to figure out what is 2.3% of 12.5. So we multiply 12.5 by 2.3 divided by 100 to get that plus or minus 0.3 meters per second. So to determine how far our final result is off, so we've done the uncertainties thing and we've done our calculation. The question is, how much is the final answer we came up with off from the expected answer? So in other words, what's our percent deviation or our percent error? You're going to use this equation pretty often in my class, so you need to know it. The percent error equation or percent deviation equation is percent deviation equals the difference from the accepted value divided by the accepted value times 100. So you subtract your value from what's accepted, you divide it by what's accepted, and multiply by 100, and that gives you the percent deviation. The way it works is if your percent deviation is smaller than 5%, then you've done a great job. If it's between 5 and 10%, you've done an acceptable job. If it's bigger than 10%, unless there's some weird thing going on with the experiment, that's not so good. So we are done. That is the end of the notes for today. Thank you for your rapt attention.